Thank you for joining today's webinar, How to Choose the Right Pyranometer to Minimize Revenue Leakage Risk. My name is Ella Joseph Kipenzonen, and I'm happy to be your host today. It's great to see so many solar and renewable energy professionals from around the world joining us today. Before we begin, a few housekeeping notes. This session is being recorded, and the recording will be shared afterwards, so you can rewatch it or share it with colleagues who might be interested. Please feel free to submit your questions in the question tab at any time during the session. We will collect them and address as many as possible during the Q&A session at the end. And as you can see on the screen, there is our agenda for today, and this is what we're going to discuss. So we will start with the fundamentals, what irradiance is, how it's measured, and the role pyranometers play in PV performance monitoring. After that, we'll move to an overview of key international standards and what they mean for sensor selection, accuracy classes, and compliance. In the next part, we'll look at how small measurement errors can translate into significant financial impacts, affecting performance ratio calculation, warranties, O&M decisions, and asset valuation. After that, we will share best practices on choosing the right pyranometer, focusing on measurement uncertainty, application needs, and environmental conditions. And before we get into submitted questions, we'll explore why long-term sensor stability and low drift are critical for PV projects designed to operate for decades, and why short-term accuracy alone is not enough. And then we'll close with the Q&A session. And here you can see our panelists today, and I'm very happy to introduce them to you all. Joining us today, Craig, Global Product Manager at Kipenzonen, a registered professional electronical engineer leading the global strategy for solar measurement solutions, and Udo, Application Development Manager at Kipenzonen, with over 25 years experience in meteorological instrumentation with a strong focus on renewable energy markets. Together, they bring deep technical, commercial, and real-world PV monitoring expertise. With that, let's get started. Udo and Craig, thank you for being today with us. The floor is yours.
Thank you, Ella. Yeah, I'm really excited about today's topic. I started my career off in designing industrial automation systems for solar PV plants. And so I know that we're talking about something that is really small in the grand scheme of a utility scale solar PV project. But I also believe that it sits at the heart of many performance calculations and many commercial decisions that are made about the asset. And that is obviously pyranometers. So I'm going to walk us through a bit about how they're used to measure irradiance and why the quality of that measurement actually matters far beyond the instrument itself. So let's get things kick-started with a brief overview of irradiance and pyranometers. So on the next slide, we'll see that this may come across as a bit basic to many, but I think it's worth running through the fundamentals. It does start with the sun, which emits electromagnetic waves across a broad spectrum that includes ultraviolet, visible light, infrared, and together this is what we call solar radiation. Now, irradiance is a measure of the power of this radiation arriving at a particular surface, and that is why it is expressed in watts per square meter. I like to think of this as the fuel supply for a solar PV plant, and so everything that the plant produces essentially starts here. For solar PV modeling and performance monitoring, we need to measure irradiance across multiple surfaces. There are two very important ones. That is global horizontal irradiance, or GHI, which is the total radiation arriving on a horizontal surface. And then plane of array irradiance, or POA, which is the radiation arriving at the tilted surface of a PV module. There are also the reflected equivalents of these, which would be RGHI and RPOA, and these are measuring the upward facing and rear facing irradiance respectively. Other important measurements are diffuse horizontal irradiance, or DHI, which measures the scattered radiation from the sky, excluding the direct beam from the sun, and albedo, which is the ratio of the reflected to the incident irradiance. Both of these are critical for bifacial systems. Now, irradiance sits at the center of so many commercial discussions about solar performance because it is a key element of the denominator in the performance ratio, which is the most fundamental measure of how well a solar plant is operating. PR is essentially the ratio of actual power output against the expected theoretical output. And to know what was the theoretical possibility, you need to know how much irradiance arrived. So any error in that measurement compounds directly into every performance metric, every yield model, and every decision that depends on them, essentially. And so pyranometers are used to measure irradiance. Thermoelectric pyranometers specifically are the industry standard and only bankable means to measure irradiance for solar PV modeling and performance monitoring. Now, radiation hits the pyranometer detector, which is at the center, and it creates a temperature rise across a highly sensitive thermocouple, which then generates an electrical signal which is proportional to the incoming radiation. Now, there are some critical elements to the pyranometer that enable the efficacy of the sensor. One of these would be the dome, which is made of a special type of glass so that it is spectrally selective. And what this means is that it transmits the solar spectrum through to the detector while simultaneously blocking thermal infrared from the surrounding environment. And now this is very important because it means that the sensor is responding to the solar radiation specifically and not to any ambient heat around it. The housing ensures that there's thermal stability across the entire instrument, and the feet and bubble level are critical for ensuring the pyranometer is installed exactly in line with the surface whose irradiance it is representing. And this is something we'll return to when we discuss misalignment. And so, standards. Pyranometer design, pyranometer selection, and the use of pyranometers are governed by two main standards. One of them is the ISO 9060, and the other one is the IEC 61724-1. So ISO 9060 was first published in 1990, and it was most recently revised in 2018. Now, this is the standard that defines all the required performance criteria for radiometers, and that includes pyranometers. And it classifies instruments across operating classes based on how well they actually meet these different criteria points. So one of the key concepts that is introduced in the 2018 standard is spectral flatness. And this is the requirement that a Class A instrument has uniform sensitivity across the solar spectrum. This essentially means it gives the same response irrespective of which wavelength of solar radiation is hitting it. And this matters because the spectral composition of sunlight changes with atmospheric conditions and cloud cover and sun angle. And so if you have a sensor that is more sensitive to some wavelengths than others, it will produce a bias that varies with these conditions. And this is very hard to detect and almost impossible to correct. The 2018 edition of the ISO standard moved away from old terminology, such as secondary standard, first class, and second class, and moved towards more simple terminology, which is Class A, B, and C. Class A is the highest accuracy, and Class C is the lowest acceptable accuracy. The standard prescribes around 11 different performance criteria. Some of these criteria include, or some of the criteria included is directional response, nonlinearity, temperature response, zero offsets, and these are some of the more commercially significant ones as well. Each criterion defines the operational guardrails of a device, and those guardrails must be met in order to achieve a given classification. Um, each of these operational guardrails also contribute to the overall measurement uncertainty of the device. There are a few key things to mention about overall uncertainty. There is the calibration uncertainty of roughly 1.2%, which is also governed by the ISO standard and forms part of the total estimated uncertainty. The rest of the components of this total estimated uncertainty is determined by real-world operating conditions. So ISO 9060 does not actually specify a single daily uncertainty figure directly, but it specifies the individual performance criteria which contribute to this overall uncertainty. And the other thing to note is that Class A is a floor. It's not a ceiling. Not all Class A pyranometers are equal. Some instruments significantly exceed the Class A specifications, and this leads to less uncertainty in the overall measurement. So, as I mentioned, if the ISO standard governs what the pyranometer is and how it needs to perform, well, then the IEC 61724-1 standard governs how the pyranometer needs to be selected, operated, and maintained to ensure that the data that it is generating is reliable for PV plant performance monitoring. And so, like ISO, the IEC standard has different classifications, but the distinction is important. ISO is concerned with classifying the device, and IEC is concerned with classifying the monitoring system the device operates within. So to have an IEC compliant Class A monitoring system, you must use an ISO 9060 Class A pyranometer. But that's only the starting point. The IEC standard also specifies how those instruments must be installed and calibrated and recalibrated and cleaned and operated. Um, the, the consequences of not meeting IC Class A requirements is directly commercial. Performance data generated by non-compliant monitoring systems cannot be relied upon for lender reporting or secondary market transactions. And so it's not a technical shortcoming, it's a data integrity problem that comes with a commercial price tag. And this is the bridge into everything we're about to discuss. So let's take a look at revenue leakage. And so IC tells us which pyranometer to use and how to use them. And we're now going to take a look at why that is the case and what costs come up if you don't follow it. So the framing I want to establish here, and I hope that this persists throughout the presentation, is that irradiance measurement quality is not an instrumentation concern. It is actually a commercial concern that happens to originate in the instrument. And it is a concern that needs to be considered throughout the entire life cycle of a solar PV project. So in 2019, there was a solar risk assessment, and in that, DNV analyzed utility scale plants, and they found that they were underperforming financial models, or financial model expectations rather, by around 3% on average. And so in 2020, they ran another study looking at commercial and industrial scale plants. And in their 2020 analysis, they found that financial model irradiance assumptions tended to overestimate long-term average irradiance by around 2%. And this was leading to expected revenue underperformance of the same degree. In that same report, Kilowatt Hour Analytics added a further dimension. So their analysis found that P90 production events, which by definition should occur once every 10 years, were actually occurring roughly once every 3 years. That tells us that the P90 baseline itself was being set too optimistically, compounding the overestimation problem. They went on further to conclude that when a project delivers at its true P90 rather than its modeled P50, equity cash yield would fall by approximately 50%. And that's not because revenue fell by 50%, but because of how debt service interacts with equity in typical capital structures. And so these two data sets together describe the financial architecture of the risk of overestimation in performance modeling. And they highlight the central role that reliable irradiance measurements plays within it. But the exposure is further exacerbated by inaccurate measurements throughout the operation of the plant, which further skews performance metrics. So I want to take a moment to build up the numbers from first principles, because it's worth being precise about what this exposure estimate on the screen represents and where it comes from. And it's a high level theoretical example. Let's assume a 100 megawatt plant running at 25 capacity factor that would generate about 219,000 megawatt hours a year. And if we have a $40 per megawatt hour PPA, which is relatively conservative, that would lead to approximately $8.75 million in annual revenue. Now, assuming a one-to-one impact and we take a 1% irradiance bias, that would reduce annual revenue by $87,500. And if we take that loss and we discount it over 25 years at a discount rate of 5%, then the net present value of that direct energy loss is approximately $1.2 million. That's the high level estimate cost of 1% measurement error in pure energy terms. And it maps very closely to a case study we presented in our blog earlier this year, where we showed a 64 megawatt plant with a 4% PR deviation incurring about $1.8 million losses over 30 years. So as we saw on the previous slide, the direct energy loss is only a part of the full exposure. So since debt service is fixed and doesn't adjust when revenue falls short, it is equity that absorbs all the variance below the debt service threshold. And so a 1% irradiance bias, if indeed meaningful, could see equity yields fall far greater than 1%. The financial structure amplifies the measurement error well beyond the raw energy loss. And this is what was being demonstrated by Kilowatt Hour Analytics in their report. Now we could go a step further and layer in asset valuation effects. If we take a discounted cash flow model built on 5 or 10 years of performance history that has a systematic irradiance bias embedded in it, it produces a valuation that does not reflect the plant's true productive capacity. And that will correct itself at refinancing or at exit or at the next technical due diligence, but somebody will bear that cost. And all of a sudden, the direct energy net present value impact of $1.2 million turns into a total exposure that is materially larger than the energy loss alone suggests. If you scale the size of the plant and the measurement bias, and all of a sudden these numbers become significant. Ultimately, the measurement bias could potentially cause problems that run into the millions of dollars. And so, if we accept that there is a risk of revenue leakage through inaccurate irradiance measurements, then we need to understand where those inaccuracies come from and what they cost. And if we're looking at pyranometers, we can look at 4 different sources. This is not exhaustive, but these are 4 major sources. The first being the inherent bias in the pyranometer measurement, which is the measurement uncertainty built into the pyranometer under real operating conditions. To be clear, this is not a failure of the instrument. This is just the reality of measuring solar radiation in varying atmospheric conditions. But this is the baseline from which all other errors do compound. Second is misalignment. If the pyranometer is not coplanar with the surface that it's measuring, then the irradiance it captures is geometrically different from the irradiance arriving at the panels. And so a deviation of just 1 degree can push average measurement uncertainties up by 1 to 2%. And this is one of the most common and most avoidable sources of errors. It's one of those that is frequently introduced at installation and commissioning, and sometimes never gets corrected. The third one would be sensor soiling, and this is dust or pollen or moisture or other contaminants building up on the dome and reducing its transmissivity, which then depresses the irradiance reading and inflates the plant performance. And soiling can have an impact of 1 to 3%, depending on soiling intensity and the frequency that cleaning occurs. And then finally, we have undetected sensor drifts. And now all pyranometers drift over time because the thermocouple will age. And without regular recalibrations, this drift goes undetected. It's slow, it's directional. It doesn't look like noise, it just looks like stable but slightly wrong baseline. And so over time, this drift leads to larger measurement uncertainties if it's not corrected. And the final thing to state is that these sources are not independent, they stack on each other. A sensor that is slightly misaligned, lightly soiled, and operating beyond its calibration interval is accumulating errors from multiple sources simultaneously. And the commercial consequences differ depending on the direction of the error. So if you have phantom underperformance where the plant looks worse than it is, then you might have O&M, you might trigger O&M escalations, or there might be penalty clauses, EPC warranty provisions that is ultimately sending money out of someone's pocket immediately. And if you have phantom overperformance where the plant looks better than it is, which that sets a baseline and real faults go undetected. Soiling is not caught, degradation is understated, and the asset is valued above what it is actually sustaining. So I want to say that I think this makes a strong case for how this small, relatively inexpensive sensor is indeed one of the most financially significant instruments on the entire site, because systematic biases don't average out like noise does. Random noise, the kind that you get from atmospheric turbulence and short-term fluctuations, they average out, but systematic bias does not. The pyranometer that consistently reads 1% high reads 1% high every hour, every day, for the rest of its life, and it compounds into every performance metric, every yield model, every commercial decision made about the plant. And the longer it goes undetected, the longer you have decisions being made based on a corrupted baseline. And this is the reason that choosing the right pyranometer matters. Not because a better instrument is expensive, but because the cost of the error it prevents is orders of magnitude larger than the cost of the instrument itself. And so in conclusion, I think a fitting summary is this. The sensor may cost a few $100s. The maintenance will probably cost a few thousand, but any error, if left unaddressed, will cost millions. And I hope that this illustrates why pyranometer selection and maintenance is not a procurement detail, but rather a very important commercial decision. And with that, I am very delighted to hand over to Udo to help us understand how to go about selecting the right pyranometer.
Yes, thanks indeed, Craig, for the great explanation. I guess that's making my life now much easier because everybody has already understood what I'm talking about now. What I would like to walk you through is some criteria about how to choose the right pyranometer for your application. And this is first and foremost its accuracy and uncertainty, where we have already heard a lot about now. A pyranometer's uncertainty especially matters when your business model is strongly depending on an accurate performance ratio calculation, like it is the case when you're an operational maintenance company and you need to guarantee a certain performance ratio to your client. and this even more the bigger the plants are getting. So before we dive deeper into this uncertainty consideration, let's first of all have a close look on how performance ratio is defined. And here on the slide, you can find a formula from the IEC standard. So in general, performance ratio is defined by the difference between the actual energy yield of a PV plant and the expected energy based on module type and environmental conditions like irradiance and temperature. So this basic formula is about how performance ratio is calculated. There are even more complicated formulas like for temperature corrected performance ratio or bifacial performance ratio. So let's stay with this one. This is complicated enough, I would say. The important in-plane irradiance, or also called plane of array irradiance, can be found in the denominator of the equation, here marked in red. And even though I was always pretty bad in mathematics, it's very clear if there is a higher uncertainty in irradiance measurement, then automatically there will be a higher uncertainty in performance ratio calculation as well. So the more important and accurate performance calculation for your business model will be, the lower the uncertainty of the irradiance measurement or the uncertainty of the pyranometer needs to be. So that's pretty clear. Next slide, please, because let's put the uncertainties of different instruments into numbers. So Craig has already explained some details of the ISO 9060. And here in this table, you can see in the outside left column, there are the parameters from ISO 9060 that define finally the quality of the pyranometer. I focused here on exclusively class A pyranometers and left out the classes Bs and Cs, and as well as the silicon sensors. And on the outside right column, this is what the standard specifies as a minimum threshold. And in the inner columns, they show the minimum performance of 3 different Kippensonen class A pyranometers. So it's the SMP10X, the 12, and the 22X. And the bottom line, finally, that sums up, let's say, all threshold to a maximum error scenario at an irradiance of 1000 watts per square meter. And when we compare now the standard requirements against the pyranometer's performances, then you will find out 2 things. First, all Kippensonen pyranometers perform clearly better compared to what the ISO 9060 requires, but that's obviously not really a surprise. But second, there is a significant performance gap even between the class A pyranometers, depending on their design and calibration efforts. Or in other words, there are better pyranometers and even better instruments within the class A specification. And that could be used also for performance ratio calculation optimization. And let me give you an example about Kippensonen, the SMP22X, which actually provides the lowest uncertainty in the market, because for the longest time, the SMP22 was supposed just to be made for, let's say, highly sophisticated applications in meteorological science or in climatology. They were made more or less handmade in quite low quantities, but now, due to its extreme low uncertainty, it's also used in PV performance monitorings. For example, in these huge gigawatt plants like they are built in the Middle East or other parts in Asia. So on the right side picture, you can see an SMP22 example on the Al Dhafra plant in the Emirates, was commissioned, I guess, in 2022 with 2 gigawatts. In these days, the biggest plant on the globe. And on the left side, you can see a historical overview about how uncertainties of Kip-Zonen pyranometers have improved over the years and even over the decades. So a second criteria about how to choose the right pyranometer is also how pyranometers behave under different ambient conditions. And the IEC standard, the IEC 61724, also contains one chapter about the so-called dew and frost mitigation for irradiance sensors. And this is required for Class A monitoring systems and location where more than 2% of the annual irradiance hours are affected by dew and frosts. And the outside left picture shows a situation where the modules are covered with a dew layer in the back in the early morning hours. And this, of course, will lead to a delayed ramping up of the plant performance until the rising sun has burned away the dew layer. But on the other hand, in the front, you can see the pyranometer's dome is absolutely clear. And the reason for this is that we have used here a pyranometer with an integrated heating, which is the case for the Kip-Zonen SMP12. How it is shown on the right, outside right picture in this infrared image. And this effect is even more relevant for negative temperatures when the dew turns into rime or frost, which impacts the pyranometer's performance in a significant and even unpredictable way when there are frost and ice layers on the glass dome. And finally, there is a third selection criteria for pyranometers, and this is their long-term stability. We now heard a lot of accuracy and uncertainty, but these are of no value finally when they are not long-term stable in parallel. So when I think about these non-funded PV projects that are calculated over a period of 30 or even 40 years, then of course irradiance measurement should be able to withstand the conditions, the ambient conditions in a similar period. Okay, long-term stability can be put into specifications like a yearly drift or in a drift over 5 years. But the real proof, finally, for long-term stability comes with long-term experience. And Kip-Zonen does have this experience. One proof for that could be that we are going to celebrate a very special anniversary next year. It's called 100 Years Pyranometer. So you can see the first one built in 1927. And now we have launched the new improved Kip-Zonen X series with less than 0.5% drift within 5 years, which results not just in 5 years warranty, as it is the case for a longer term, but also in 5 years recommended calibration interval. And with a proof of more than 100,000 of units across all climate zones on the globe, we simply do not have to claim that we are long-term stable. We simply know it. And just recently, I had an example. We have received a unit from the early 1990s from a German research institute, which is still in operation. And that proves, of course, also our long-term, or let's say our legacy in long-term stability. So in the end, I would like to keep that, or I would like to ask you to keep in mind the following 2 basic key takeaways. First one is best accuracies and best uncertainties are useless when they are not long-term stable. So in other words, it doesn't help when a specified uncertainty of a pyranometer just survives for a 2 years warranty period. And the second is the power of precision only counts when it's backed by the promise of long-term stability. And with that, I guess I hand over to you back, Ella.
Yes, thank you very much, Udo. Thank you, Craig, for all those insights. I'm looking at the time. We have a few minutes for a few questions, but please don't hesitate to add them in the question tab. So even if we don't manage to cover your questions in today's session, we are going to follow up on them in the upcoming days. So maybe let's start with the first one. Udo, I think that's going to be one for you. You've mentioned Class A pyranometers, and they are not the same, but they are all of the Class A pyranometers. Could you elaborate on that? So how shall our listeners choose the right one? What's the difference if they're all Class A pyranometers?
Yeah, maybe we can switch back to the slide 19, where we did this uncertainty propagation. So within the specified parameters of the ISO 9060, we did, let's say, a sum up of all the worst case scenarios. And in the bottom line, once again, you can see this is in the worst case, the ISO 9060 would allow a maximum error of plus minus 2.6%. And within the Kippensonen pyranometer range, the Class A range, you see, okay, all of the pyranometers, of course, are significantly better than that, but within the Class A specifications, there are even some significant improvements or let's say gaps from the S&P 10, let's say as a standard pyranometer, to the heated S&P 12 with an even better maximum error behavior. And finally, the highest class standard on the market, the S&P 22 with 1.3%. So coming back to Craig's uncertainty or let's say profit loss calculation, there is a big gap just coming from the uncertainty of even Class A pyranometers, and the bigger the plants are getting, the more relevant even these uncertainties are for performance ratio calculation and for the decision on how to choose the right pyranometer.
Okay, great. Thank you so much. The next question would be about the different ISO criteria. Craig, this one will be for you. What are the most important criteria to think with respect to the overall uncertainty of a pyranometer?
Yeah, it's a good question, and I think it falls in line with exactly what Udo was saying. And if we go back to that slide, we'll actually see, or you can see the percentage contributions. The slide that you presented for Udo, slide 19. I mentioned them in my slide as well, so things like the zero offsets, which is the thermal influence on the detector itself, and directional error. Those are the ones that I listed because they're the massive contributors. But if you look at it on paper as a percentage contributor, you can understand why. So directional response for S&P 10, which would be a entry-level Class A, is the highest, one of the highest uncertainty contributors. The same goes for the thermal offsets, so zero offset A and B. And these are the exact parameters that we have optimized in the S&P 12 and 22. So you can see that by optimizing these big contributors, we're able to pull down the uncertainty of the entire device. And that is all to say that, yes, there's 11 different parameters, but they're not all equal. Some are weighted more than others.
And why do pyranometers not have an absolute uncertainty value?
Again, a very good question. And that's because the overall uncertainty is dependent on so many different factors. So what we're seeing right now is a simulation of 100 or 1,000 watts per square meters at a particular temperature range. And to do this, we've also assumed where this pyranometer is located, what time of day this measurement is being taken, and the environmental conditions around this pyranometer. As the conditions change throughout the day, as the zenith and azimuth angles change, you're going to have different conditions and your uncertainty is going to fluctuate higher and lower. What you see in the ISO standards is the absolute maximum that it can go to. What we put in our data sheets is the maximum that we're guaranteeing in our devices.
Okay, now another question would be about one of the sources of the revenue leakage. We've mentioned about recalibrating. How often should I actually be recalibrating my pyranometer? Would like to take this one.
I guess I can jump here because it has something to do with long-term stability in the end. The answer to the question is simply it depends, because if you are obliged to some certain standards in the market, like the IEC standards, so if you need to be compliant to this standard, especially to the Class A specifications, then you simply need to recalibrate the pyranometers every 2 years. That is written down in the standard. We can put a question mark behind it if it's useful or not, because as we have seen, this 2 years recalibration interval is just set into stone, more or less. It has nothing to do with the technical or with the physical performance of the pyranometer. As we have seen, the pyranometers are much longer stable than just 2 years. So in the meantime, for the new series, we have a recommended manufacturer's recalibration interval of 5 years. But in the end, if you need to be compliant to a certain standard like the ISO 61724, you need to recalibrate it every 2 years. So as I said, it's a question if this is useful, but yeah, in the end, it's what it is.
Great, thank you. Another question would be quite interesting. Wouldn't a plant operator like to yield more energy than projected by his instruments and forecasts? In that case, underestimating instruments would make the PV plant performance look better.
It's a very good question, and the answer is it depends, which is not a great answer, but it does depend, because what it depends on is who that operator is. If it is an owner operator, so somebody who has invested money into a plant and is owning that plant and operating that plant to generate revenue for themselves, they're going to have very different objectives than somebody who is being contracted to operate that plant. So it really does come down to the financial mechanisms that are drawn up in the power purchase agreement, as well as who are the stakeholders involved and where does the commercial liability and risk lie, who is owning that. So for some parties, yes, it is very beneficial to generate more, and to essentially be generating more than what the instrument is showing. But what really matters at the end of the day and what is important is everybody seeing the closest reality to the truth. And I think that is a more fundamental question that everybody should be asking, because ultimately everybody is impacted by that.
Right, great. I think we have just the last question possible for today's session. We'll make sure to reply to the others after that. It's about misalignment of the pyranometers, how to avoid the misalignment of the pyranometer.
Yeah, also here it's depending on whether we are talking about the so-called global horizontal irradiance, when the pyranometer is aligned in horizontal position, For this case, every pyranometer has an integrated bubble level, so you should use that, of course, to put the pyranometer really on a stable mounting bracket that doesn't provide any vibrations, for example, and then align the bubble level as good as possible, because let's say just a half a degree of misalignment can lead to 1% yeah, failure in the end, when we have the let's say bad condition in terms of the irradiance angle. And when it's about plane of array alignment, then it's also about aligning the mounting plate, first of all, into the correct position. And in the best case, you use so-called fixed feet. So this is the one feet of three that were visible in the sketch. So these fixed feet have a certain length, a fixed length, and if you use these instead of the adjustable feet, then you are sure that the detector and the instrument has the same alignment as the mounting plate underneath.
Great. Thank you, Udo. There are still some open questions regarding bifacial PR calculation or, for example, calibration. We'll make sure to cover them and make them available for everybody to look into the answers of our experts. But for now, thank you. Thanks to our presenters today for joining us today, and all the audience and the questions that we received from you and your engagement. If you'd like to stay in touch, learn more about our pyranometers, or discuss your specific application, we encourage you to connect with us via website or follow us on LinkedIn. Once again, thank you for your time and enjoy the rest of your day.
Thanks and goodbye.